Thank you very much. So thanks to the organizers for giving me the opportunity to present my work in this conference. Please, next slide. So before going further, I will just mention that the content of my talks are based on this paper, Virtually Symmetric Representations and Gauss Diagrams. And this is a joint work with Professor Valeriy Bardakov and Professor Mikhail Neshchadim. So by a Gauss diagram, I mean a finite number of circles oriented anti-clockwise with finite number of arrows whose head and tail lie on the circles. So here is an example of a Gauss diagram. So you can see, I hope you can see a circle and a classical node diagram. So in the circle type of diagram, just forget the labels for the time being. The diagram that we get after forgetting the labels is actually a Gauss diagram, and it is a well-known result that to every classical node diagram we can associate a Gauss diagram. Since I'm not able to share the slides, I will not be able to properly explain the procedure. But the idea is that we fix a base point on the classical node diagram, and we note down we label the crossing with some numbers, say 1, 2, 3, 4, or say X, Y, Z, and we label and we also note down the signature sign of the crossings. And then we start moving from the base point in the direction of the node diagram, and we keep noting down the sequence of the crossings along with the information that we are passing under the arc or over the arc. So and we note this sequence on our circle with the mark where we have also a mark point, and we note down the sequence, and at the last we will join the crossings from with arrows where arrows point from over to under crossings. Okay. And it is a well-known thing that not every Gauss diagram comes from a classical node diagram. Please, next slide. Thank you. So here is an example. So this Gauss diagram doesn't represent any classical node diagram. The reason is that the arrow which is at the point number 1 is intersecting odd number of arrows, and this never happens in the case of Gauss diagrams that come from the classical node diagrams. So based on this, Professor Kauffman introduced a generalization of node theory. Basically, he extends the class of nodes to virtual nodes by defining some equivalence relations on the Gauss diagrams. There are other ways to define virtual node theory, but we will focus on this aspect. So by a virtual link, we mean a Gauss diagram up to the equivalence relations generated by a finite sequence of these moves. These moves are basically counterparts of Redminster moves in the classical case on the Gauss diagrams. Next slide. And there is a planar analog of Gauss diagram in terms of the node diagrams, and we call those diagrams as virtual link diagrams. So here is an example. So it is basically generic immersion of an oriented circles where the double points are either classical crossings or virtual crossings. Next slide. And so the thing is that we have a virtual link diagram, and we want to study the notion of virtual nodes on these diagrams instead of Gauss diagrams. So basically, we need to understand how the moves in the Gauss diagrams reflect in this case. So basically the moves, so here we have different kind of moves. In the first row, the moves are basically of classical Redminster moves, and in the second row, these are basically moves which only involves virtual crossings. So the first move VR1 basically correspond to the analog of classical Redminster first move in the virtual case, and similar to the second and the third one. And the last one is basically the mixed move, which involves virtual crossings as well as classical crossings. The one thing we should here we need to point out is that while we construct Gauss diagrams from the node diagrams, we never take into account the virtual crossings, and one can easily see that the moves in the second and the third row has no impact on the Gauss diagrams. Next. And similar to the classical case, each virtual node diagram is basically we can find an equivalent diagram which is coming from the closure of a diagram which we call as a virtual braid diagrams. So these are basically just similar to the classical braids, but the only difference is that along with the classical crossings we also have a virtual crossings. Next, please. Now we said that two virtual braid diagrams, we say they are equivalent if they are related by these moves. So the moves are similar to the moves that we have mentioned in the case of virtual node diagrams, but the only difference is that we have removed the first moves, the first classical Redminster move and the first virtual Redminster move. The reason is that in the virtual braid diagrams, the arcs are basically monotones, so we never encounter those moves. And we say that the equivalence class of a virtual braid diagram is a virtual braid. Next, please. Now we define a virtual braid group to be a collection of braids on n strands, where the group operation is basically is basically placing one braid over the other, and then we rescale the length of the strands. And any virtual braid diagram can be decomposed into these elementary braids: sigma I, sigma I inverse, and rho I. Next. Thank you. So here is an algebraic description of virtual braid group on n strands. So it have a presentation where the generators are sigma 1 up to sigma n minus 1 and rho 1 to rho n minus 1, and the relations. So the relations in the first two relations are basically coming from the classical braids. Basically in the first bullet point, the second relation is basically just the third Redminster move on the classical crossings. And the relations in the second bullet point are basically correspond to the virtual crossings, to the virtual Redminster moves on the braid diagrams. And the last one are basically mixed move and the far commutativity. Next one. So now we come to the main object of the talk. By a representation of braid group, we mean a morphism from the virtual braid group to the automorphism of some group or a module. And if we have a presentation of the group H or a module H like this, then we say the representation is virtually symmetric if the action of the row i's is of permutation type on these generators, on the generators H1, H2, and H2. Okay. And we say two representations are equivalent if the one can be obtained from the other by conjugation from an element of odd H. Okay. We have shown that these four well-known representations are actually equivalent to virtually symmetric representations: the generalized Artin representation, Silver-Williams representation, Borden-Dice representation, and extended Wada representations. Next. Okay. So basically, we will focus on this particular representation, phi m. This was constructed by Bardakov et al. Here Fn denotes a free group on rank n, and Zn denotes a free abelian group of rank n, and Fnn denotes the free product of these two groups. One can easily see that this no previous one can the previous one yes. So one can easily see that the action of row i's on the generators is not of permutation type, but we have shown that it is equivalent to some representation which is actually virtually symmetric. Now the question is that why we are interested in these and not on the previous one that we have shown virtually symmetric. The reason is that those representations are actually can be in some sense they can be derived from this representation. So basically the reason is that there is a Bardakov et al. Constructed a representation which was generalization of those previous 3, and this representation is actually a representation which comes from that generalization. So we will focus on this representation. Next one. Thank you. So phi s is a representation which is equivalent to the representation phi m, and it is easy to see that the action of rho i's is of permutation type on the generators. Okay. Next one. To any representation from virtual braid groups to the automorphism groups of some groups or modules, we can to each braid we can associate a group which we denote by G sub phi beta. So it is nothing but a representation of the group H with additional relations. That is, Hi is equal to H, the element which we obtained by the action of braid beta on the HIs. Okay. And we have shown that the group GM beta is isomorphic to GS beta. So M correspond, GM beta correspond to the group that we associate to the braid beta using the representation phi m. And similarly, I hope it is clear what is GS beta. And we have shown that these groups are basically virtual link invariants. Now the question is that if these two groups are isomorphic, GM beta is isomorphic to GS beta, then why we are bothering about the this second form GS beta? And we will answer this in next slide. Next one. Thank you. So our aim was to recover the group GM beta using Gauss diagrams, and we cannot do it unless the action of the rho i's on the generators of permutation type, because in the Gauss diagrams we never take a virtual crossing into account. That's the reason. So here we are describing the group that in the previous slide that we have mentioned about GM beta in terms of Gauss diagrams. So where the Gauss diagrams is basically one can think of as a Gauss diagram correspond to the closure of the braid beta. Okay. So the procedure very simple. We have a Gauss diagrams of consisting of M circles. Then we label these circles with elements V1, V2, Vm, and we cut the circles at the head and tail of each arrow, and we label those arcs, the obtained arcs, with variables x1, x2, and xn. Okay. Now the group. Now we associate a group pi d to the Gauss diagram D, which is defined by representation of this x1, x2, xn, and v1, v2, vm are the generators, and R is a set of relations which is coming from each arrow in the Gauss diagram. So the relations are of this. So the relations are shown in the figure. So if the arrow is positive and pointing from the jth circle to the ith circle, then we have two relations that is written below the diagram. And similarly, if the arrow is negative, then we have two relations. And we have further relation that of commutativity between the variables vi's. And this group is actually is isomorphic to the group GM beta, where the Gauss diagram is representing the closure of the braid beta. Next one. Thank you. Now we come to the second main object of the talk, that is Mark-Gauss diagrams. These are basically the Gauss diagrams, but with additional features. That is, besides arrows, we have these noted points labeled denoted by these dots with signatures plus and minus. So we call Gauss diagrams in these additional features as Mark-Gauss diagrams. Okay, and I'm not going to so one can actually come up with the notion of marked link diagrams, which can be thought as a planar analog of virtual nodes or classical link diagram, virtual link diagrams. Okay, but we have defined this, but I'm not going to into this aspect. Next one. So we will study these diagrams that I'm calling as Mark-Gauss diagrams up to the finite sequences of these moves that are in the figure, labeled as Mark-Redmister moves. So the first and the moves in the first row and the second row are actually the moves that we inherited from the Gauss diagrams, and the moves in the last one are some additional moves. And notice that Gauss diagrams up to the Redmister moves, the set of Gauss diagrams up to the Redmister moves is properly sitting inside the set of marked Gauss diagrams modulo marked Redmister moves. The reason is that in Gauss diagrams we don't have any node points, so the moves in the third row have no effect on the Gauss diagrams, and this basically implies that this is actually a proper the study of Gauss diagrams up to these moves is a proper generalization of virtual node theory. Next one. And now we are interested to construct some invariants. Basically, we will construct a group invariant of Gauss diagrams such that it gives us the same group that I have mentioned in the previous slides for the Gauss diagrams. So the procedure is just analog that we have done in the case of Gauss diagrams. We have n circles, we cut them, add the arrows and the node points, and we label each circle as v1, v2, vn, and the arcs as x1, x2, xm. And we will define a group by a presentation with variables x1 shown up to xn and v1 up to vm with some relations, and where the set R is basically collection of relations that is coming from each arrow and each node point. Notice that node point induces only one relation, but each arrow induces two relations. And beside that, we have additional relations of commutativity between the variables vi's. And since it is easy to observe that there is nothing technical here, since Gauss diagrams have no node points, this construction, when restricted to the Gauss diagrams, gives us the same group that we have mentioned in the previous slides. Next one. So here is an example. So here is an example of the group associated to a Gauss diagram. The only thing I will here point out is that just notice that B is conjugate to A, C is conjugate to B in the relations, and so on. So basically they are conjugate in a cyclic manner. That is the one thing. The second thing is that if we notice carefully, then each generator except the generator V is conjugate to generator A. And the last thing is that the abelianization of this group is free abelian group of rank 2. Next one. Now we define C1 groups. In terms of presentation, we say a group is C1 group if it have a presentation where the generating set is Y and which have relations of these kinds: Wij's, Xi, Wij's is equal to Xj. And such presentations we call as C1 presentation. And the group corresponding to this presentation is known as a C1 group. And we say C1 group is irreducible if its abelianization is of rank 2. So the groups that we are associating to Gauss diagrams to just one component are basically C1 groups and irreducible C1 groups. That's all. Next one. So I will just focus on the theorem. So basically we have shown that in the proposition we are saying that if we have any one circle Gauss diagram, then the group that we are associating to it is basically an irreducible C1 group, and its deficiency is either 1 or 2, and its second integral homology group is cyclic. So here by definition of a presentation, I mean difference between the number of generators and the relations. And the deficiency of group means we are looking at the maximal of number of the deficiency among all the finite presentations of the group. We have also shown in the theorem we are saying that if we are given any irreducible C1 presentation which is of deficiency either 1 or 2, then we can find a Gauss diagram whose group is that group, is the group that we have in the theorem. Next one. I will like to skip this one. Next one. This is just a proof of that theorem, but since I don't have the slides in my hand, so I will avoid the going to the proof. Please, next one. Furthermore, we have defined a peripheral structure for the Mark-Gauss diagrams. The idea is that if we have a Gauss diagrams with Mark-Gauss diagrams with n components and pick any component, then for that component we will define the meridian and the longitude pair. The idea is that fix a base point on any arc of the chosen component. So here I am saying it is the kth circle, and the generator corresponding to that arc where the base point is lying, we say it is a meridian, and we are denoting it by mk. Now the thing is that how we are going to write the longitude. So the idea is that we start moving on that component. So basically in the slides, that component is basically the kth circle, and there are 4 figures. In the leftmost figure, we are saying that if we encounter an arrow with head on the kth circle, then we write a word like illustrated in below that figure. And if we encounter an arrow with sign negative, then we write a different word, and that word that is below that figure. And if we encounter a tail of an arrow, then we are not bothering about the labels of the arcs. We will just write VT epsilon. Okay. And if we encounter a node, again, we are not bothering about the label of the arcs, and we just write VK epsilon, where epsilon is equal to eta. Okay. And at the last, we will write MK minus alpha, where alpha is the sum of sign of no arrows whose head lies on the kth circle. Okay. And so this actually not only gives a peripheral pair for the Mark-Gauss diagram, but also we are actually explaining the peripheral pair for the Gauss diagrams also, because they are actually Mark-Gauss diagrams now. Next one. So here is just an example. I would like to skip this one. Next one. Let's come to the main, the second main theorem. So let's suppose we have a group G with an irreducible C1 presentation of deficiency 2. Then we are saying that we can find a Mark-Gauss diagram with the whose associated group is the group G, such that the longitude is trivial. In particular, if we have a classical node K, here pi1 ck, I mean the node group, that is the fundamental group of the complement space of the node in the 3 sphere. And here we are taking its free product with free group on one variable v. We are saying that we can always realize this group as a group of some Mark-Gauss diagram such that the longitude is trivial. Okay, but that's actually important, because every classical node is now basically is an element in the equivalence class of Mark-Gauss diagrams, but there it always have a non-trivial longitude. The longitude is actually the same thing that we have in classical nodes, but here we are emphasizing that besides that we can also find a Gauss diagram with trivial longitude, but it is a non-trivial element in the equivalence classes. Next one. So here I will like to just wind up. So it is a classical problem in node theory that to study the homomorphic images of the node group by knowing the images of the meridian and longitude. So we are for reformatting that problem in case of the Mark-Gauss diagrams. So let G be a group, and mu and nu are elements in the group G. The question is, does there exist a Mark-Gauss diagram D with the surjective homomorphism from the group that we are associating to the Mark-Gauss diagrams to the group G, such that meridian maps to the element mu and the element V maps to the element nu. So we basically correspond to just a single component in the Mark-Gauss diagram. So here in the problem, the Mar-Gauss diagram is basically just a one component Mar-Gauss diagram. Okay, they don't have more than one circle. The thing is that it is easy to notice that in this case, the group G is must be finitely generated by nu and conjugates of mu, because we need to satisfy the relations that we have in the case of group ID. Okay. We say an element in the group G is realizable if we can find a Mar-Gauss diagram D and a representation rho such that the lambda is image of the longitude. Okay. And we call this collection of elements as a realizable elements, and we are denoting it by lambda G. And we have shown that this group is actually a subgroup of G. The last one, next one. Thank you. So here are some questions. So the important question at this point is that does there exist a representation of the virtual braid group which is not equivalent to any virtually symmetric representation? So far we have not been able to find any or construct any such representation. Why this question is important is that if we have a representation which is actually equivalent to the virtually symmetric representation, then it basically, in some sense, I'm not saying it in proper words, I'm just saying that in some sense it means that the virtual crossings have no effect on that on the invariants that are coming from that representation. Okay. And the second thing is that since we have defined the peripheral structures, we are interested to understand how these structures can help to distinguish virtual nodes different from the structures that are defined by the Kauffman, but that were defined by Professor Kauffman. And the last thing is that we are also interested to know if there exists any interpretation of these Mar-Gauss diagrams as codimension 2 embeddings. The thing is, I just want to mention is that, of course, one can come up with the notion of abstract link diagrams as we have in case of virtual nodes. But we are interested in knowing the codimension 2 embedding interpretations. And with this, I finish my talk. Thank you for the kind attention and for the assistant to Professor Pravakar. Thank you.
Thank you, Manpreet. Any questions from the audience? So if there are no questions, let's thank the speaker. So
thank you.